we'll talk about some new perspectives. Okay, so you are looking at the world, we all are looking at the world from one perspective right now. If we change our perspective, something different will happen for everything. But we'll talk about the motion, but in particular, in physics in particular. Okay, so suppose this is one frame which is stationary. We'll call this S frame. Okay, which is a stationary frame, which is S frame. In S frame, this particle A is moving with a velocity VA. Okay, in S frame. So VA, what is VA? We should define everything. VA is velocity of A in S frame. Okay. Now there is another particle, particle B, which is moving with velocity VB compared to S. Okay, so VB is again velocity of B in S. And now you are watching both of them from the perspective of S. Now, if you want to go to the different perspective, suppose you are leftist now, and you want to go to the rightist perspective, you sit at the rightist perspective, you set your reference frame at the rightist perspective, and then you see the world from there. Okay, and you will realize that the facts are anyways facts from both ends. It doesn't matter whether you are leftist or rightist or chestist, whatever. Okay. Okay, chestist is not the word by the word, by the way. Centerist is the word. But yes, you see from the world from any perspectives, the world is the same. See it from anywhere. But in physics, if we change this perspective, if we set up a new coordinate frame S prime here, then if we see, okay, then if we see there are very fine distinctions. So this, suppose B's position vector was RB from S, B's A's position vector was RA from S, and suppose A's position vector from B now, from S prime now, is R position vector of A from B. So RAB is defined as position vector of A from B, or from the perspective of B, or from the reference frame of B. That's the most suitable physics word, from the reference frame of B. How to find out the reference frame? You attach the coordinate system with it. Okay, so these are three vectors. Now, can you see the relation between three vectors immediately? Somebody of you can see, spot a triangle addition law here and tell me. This is RB pointing in this direction. Okay, this is RAB pointing in this direction. Position vector of A with respect to B, and this is position vector of A. Can you spot a relation? Swati, if you can tell me.
RB plus RAB is equal to RA.
Sorry.
RB plus RAB.
Yes.
Is equal to RA.
RA. Yes. This is the relation that we have spotted immediately from this. So we can see that RAB from here is RA minus RB. And we know that this RAB is not constant because B is also moving, A is also moving, and with respect to S, obviously. So A is also moving and B is also moving. So RAB will also be changing. So if you take time derivatives on both the sides, so this is equation for displacements, if you see from this frame. But if you take time derivatives on both the sides, then you will immediately realize that the velocity formula is not different. You can take time derivatives both the sides, and VA minus VB is your formula. And similarly for acceleration, it is AA minus AB. These are the formulas for velocities and accelerations. They are not different. They are the same formulas you studied, but now they are in vector notations. Now they are not in one dimensions. Okay, they are in vector notations, and they are obtained by just successive time differentiation. We just take d by dt. We again take d by dt. So what is VAB? Velocity of A with respect to B is velocity of A with respect to some stationary frame minus velocity of B with respect to some stationary frame. Okay, from where we are measuring V and B. If they are also relative with some third frame, you can change it here as well. Okay, and these things, these relative velocity transformations are known as Galilean transformations. Okay, this is how you transform velocity from one frame to the other frame in Galilean transformation. They are called Galilean transformation because they are related to the Galileo's view of universe. Okay, and they are not exactly 100% accurate, as we'll know if we study special relativity. they are not 100% accurate. Yes. So are you guys able to see these formulas or not?
Yes, sir.
Yes, sir.
Yes. So they are not some out of the world formulas. Relative velocity, they are called relative velocity and relative acceleration, by the way, not some out of the world formulas. Okay. So this formula and this formula, they are useful, particularly useful in many cases. When you just change your reference frame in physics, when do we do that? Let me give you a wonderful example. Okay. So if you see a particle moving in a tunnel called Large Hadron Collider. There is a big tunnel in Geneva called Large Hadron Collider, LHC, where you have small particles like protons. You accelerate protons from both ends. It is a toroidal tunnel, actually, a toroidal tunnel. That toroidal tunnel, you accelerate proton from both ends and then they collide here. And when they collide, there are some particles which are formed. One of that particle is muon, mu minus. One of that particle is muon. Okay, and if you see muon from its own frame, so that muon, because it is formed because of two proton colliding, this muon is moving with some velocity v mu. Okay, some velocity of muon. Now if you see muon from the laboratory, it lasts for about some seconds, like 10 to 12 so about 1 to 2 seconds, or 10, about 10 seconds. Its lifetime is about 10 seconds or 1 second, 2 seconds or 3 seconds, something like that, from the laboratory, from where you see it. But if you do theoretical calculations of how much should it leave before it again decays or merges with somebody, because this muon is a very small particle like electron. Okay, so muon is very small particle just like electron, so it either merges with somebody, yes, it in all the cases it merges with somebody else. Okay, so muon just goes and attaches itself with somebody else. So for how much time can we see its free independence? It is about 10 seconds. In that Large Hadron Collider, we have a large set of data, numbers, from which we figure out that yes, it was a muon. We don't see it as a muon going here and there. We have a large set of numbers from which we figure out that yes, it was a muon indeed, from analyzing those numbers. So that is called data analysis. That is a very big part of physics nowadays, data analysis, because if you do one experiment, only a single experiment at Large Hadron Collider, it is an estimate that the data, if you collect them in the CDs, those compact discs of 700 MBs, okay, if you contain those datas in those CDs, those, and you pile up those CDs for only one experiment, one proton collision, those CDs will pile up from the ground to the moon. It is that much of data, and you need to analyze all the data to get all the information out. We are obviously not analyzing all the data. We are analyzing very specific data after that experiment, but the data's pile of that compact disks is from Earth to the moon in only one experiment. If you do it, they have a very big storage capacity, of course, where they store their data, but those data are numbers, and those data needs to be analyzed, and Indians are very good in analyzing the data. Okay, so whenever LIGO detection happened, that gravitational wave is there, the detection happened, many Indians led by Professor Sanjeev Durandar of TIFR Mumbai, they were in the background of analyzing those data. Okay, so many Indians are very good in analyzing data. So analyzing data is a new branch of physics, okay, that is related with experimental physics, but we are not going there. We are going into this frame. If you do theoretical calculations, muon should live only for a few nanoseconds, but it is living for microseconds, not for 10 seconds. I'm sorry, I'm wrong. Not for 10 seconds, but it is living for a few microseconds. And what is this difference from nanosecond to microsecond? A big difference, because if it is living for a few nanoseconds, it should travel only 1 centimeter in this pipe, but it is traveling a few meters, 10 to 20 meters in this pipe, because it is living for microseconds. You can see it is 1,000 times more, 1,000 times more. It is staying 1,000 times more. From the frame of reference of muon, it should only travel 1 centimeter distance. But if you change it to the laboratory frame, it is actually traveling this much distance. That is the difference. Okay, and this difference is obviously because of relativistic speed of muon. But their one frame is called Lev frame, and one frame is called the particle frame. So, or center of mass frame. Okay, so center of mass frame is the another frame, lab frame is one frame. So if you see from center of mass frame of muon, it is moving only for 1 centimeter or 2 centimeter. If you change the frame, if you see from the earth, it is actually moving 10 to 20 meters. That's why we are able to detect it. 1 centimeter is impossible distance to detect it, because that circumference by itself is some around 21-22 kilometers of that large hadron collider. I told you that it is a toroidal shape, and that toroidal shape's circumference is about 20 kilometers. So it is a very big circumference, and that 1 centimeter and this 1 kilometer or 20 kilometer is nothing. So you can't spot 1 centimeter there. You can spot some meters there experimentally. Those data will make sense. Okay, so that's what happens when you change the frame physically, and this is why we generally try to look at things from different perspectives. Which is always, we don't say something is wrong or right. We always talk about the frame of reference. Okay, so this is the frame of reference, and if we want to understand it in one dimension, this is understanding. This is VAB equal to VA minus VB. Let's take a very wonderful example. Suppose you are moving inside a train. You are inside a train, so this is your reference frame. Your friend, okay, you are A and your friend is B. So you are moving inside a train with velocity VA with respect to your friend, okay, and velocity of your friend, okay, there is some another person C standing on the ground. This guy is on the platform, and there is another friend who is also standing on the platform but on the other side of the platform. So this C sees you, so you are moving with velocity VA compared to C. This guy is moving with velocity VB equal to 0 compared to B. And now if B sees you, okay, I should have all three of them moving, then only this intuition will be more clear. Let's do that. Let's make this friend sit in the another rail. Okay, so this friend B is sitting on the other rail. This friend is B. So it is moving in this direction, suppose with velocity VB. Okay, now, and your friend C is sitting on the platform watching both of you. Okay, so velocity VA is compared to C, velocity VB is compared to C. And now if you see your friend, okay, now if you see, you are person B, and if you see your friend A, will it be moving towards you with velocity VA, or will it be moving with velocity larger than VA, or will it be moving with velocity smaller than VA? This is the question.
Larger than VA.
From how do you say that? Are you saying it mathematically or from your real life experience?
So both, I can say.
Sir,
Yes. Yes.
sir, can you just repeat the last line of the question?
Okay. Question is, if I see, that is the question, that if I want to see A from B's perspective, is it greater than VB, V actual velocity, or we should not say something is actual, but velocity of A with respect to ground, is it less than velocity of A with respect to ground, or is it equal to velocity of A with respect to ground? This is the question. If VB is moving like this, you see, no, both of the trains are there, both the trains are coming towards each other. You feel that the other train, if you're sitting in one train, you feel that other train is actually coming faster, because you don't realize that you have a brain and you are moving compared to something else. You just sit in the train without using any brain, then you will realize that the other train is coming faster. Always you realize this. If you are sitting on standing on the ground, that train is going slower, but if you are sitting on one of the trains, the other train is always coming faster. So VAB is always greater than VA if both of them are pointing in the same direction, in opposite direction. Both of them are traveling in the opposite direction. Can you see this or not?